Good morning, everyone. My name is Chuanbo, a senior energy storage engineer at the National Renewable Energy Lab located at Golden, Colorado. My talk today focuses on fast charging of lithium battery to accelerate the adoption of the battery electrical vehicles and the transportation decarbonization. Fast charging is becoming a very essential feature for battery electrical vehicles. It's expected the battery electric vehicle can be charged within a similar amount of time as refilling conventional gasoline vehicles. While there are some fast charge cells available, they are cost prohibitive and also probably has poor life. Today, I will first overview the transport and the damage limits of fast charging, especially depleting. Physical-based model has been used to develop fast charging strategies. Among them, please let us focus on temperature. Currently, vehicle OEMs are using both small cells like Tesla and Rivian and large cells like BMW and GM. For large size cells, thermal management requirements need to be re-evaluated for fast charging application. At the last, I will introduce an advanced engineering solution we are developing with all cell technology. Yeah, related to battery design, the materials are energy battery and the power battery. Power battery has thin electrode, low energy, and can be fast charged. Energy cells has zinc electrode, high energy, but have to be slowly charged. There are several limits in the consequence for fast charge of energy cells. First, electrolyte gradient. Yeah, large concentration and the potential gradient in electrolyte phase to support high current result in non-uniform utilization of the medium or zinc electrodes. In extreme case, electrolyte concentration approaches to zero and shut off electrolyte utilization near current collector. This may result in plating and cracking happened near separator. Two and third lithium saturation and depleting on the graphite surface. Here and the electrolyte lithium concentration close to its maximum at the surface of graphite particle. This causes excessive potential gradient and slow kinetics. This may produce depleting. On the cathode side, there may be lithium concentration depletion. So this may cause material instability and also result in cathode cracking. And in the U.S. Department of Energy actually has a aim to achieve a charging goal with achieve a goal is 300 miles on a single charge and 15 minutes or less of a charging time by 2025. It requires high energy density cells with fast charging capability. Depleting is the formation of metallic lithium around the anode of a lithium battery during charging. It causes lithium battery to fail over time. Depleting is usually associated with heterogeneity. Heterogeneity leads to inhomogeneous distribution of lithium, resulting in stress that may cause depleting. Heterogeneity can occur at a wide scale from micrometer particle up to the cell level. Some heterogeneity is a bulk response, such as electrolyte, due to its transport limitation. Some heterogeneity can be manageable, such as pressure, temperature, and the type configuration for a battery cell. In Department of Energy's extreme fast charging program, a combination with cell testing, electrolyte thermal modeling is used to investigate fast charging performance of cell with a low loading, 1.5 milliampere hour per centimeter square, and moderate loading, 2.5 milliampere hour per centimeter square. Cell with a low loading with standard extreme fast charging performance is remarkable well, even up to 9C constant current with very high Coulombic efficiency, charge acceptance, and very little depleting observed. For a moderate loading cell, however, the charging capacity is poor. For example, at 6C, constant current charge, actually also with significant amount of observed depleting. The electrochemical model has been used as feedback to experiments and provide guidance on cell design requirements to improve fast charging acceptance at 4C to 6C constant current charging and surprise depleting for cells incorporating loading beyond 3 milliamp hour per centimeter square. The electrochemical model has been validated for low loadings and moderate loading cell based on the all experiments to date, predicting a fast charging limitation such as electrolyte depletion, onset of depleting are reasonable. Model is also compared well with some recent 1C rate operando XRD measurement from Argonne National Lab. To further investigate the nature of the difference in charging behavior between the low and moderate loading cell, the overall potential at the end of the constant current charging was characterized by current interruption voltage relaxation. This analysis is focused on the distinguishing between overall potential associated with almost instantaneous phenomena, actually its impedance, and that with a characteristic time related to transport. While depleting occurred, the moderate loading cell actually exhibit a transport over potential plateauing at the rate above 4C, indicating the high rate charging acceptance is severely limited by the transport losses. The electrical model fit the measured overpotential well and is used to investigate the cause of the severe transport limitation measured for moderate loading cell at high charging rate. Extreme electrolyte concentration results in very sluggish lithium transport and poor electrolyte electrode utilization. For low loading cell, there's enough electrolyte diffusion to prevent electrolyte depletion in the anode phase, even up to 9C. However, for the moderate loading cell, the electrolyte depletion actually within the anode and high occurred at the 4C and beyond. Thus, at the higher rate than 4C, insufficient electrolyte transport result in severe transport losses and non-uniform electrolyte utilization for moderate loading cell. Actually, to meet the specific volumetric energy density and cost requirement, the cell loading is not enough. I mentioned before, it's not enough. EV cell actually must have sufficient high loading of 3 up to 5 milliampere hour per centimeter square. The electrochemical model is used to investigate the various approaches to enable extreme fast charging without depleting for cell with a loading of 3 and 4 milliamp hour per centimeter square. This figure illustrates the model prediction for achievable energy density during 4C and 6C, charging to 4.2 volts for cells with a loading of 3 milliamp hour per centimeter square. The white section of the bars actually represent where model predict depleting will occur. Elevated temperature 45 degrees Celsius, reducing electrolyte tellurosity and improve electrolyte transport are shown to be suitable strategies. Increasing the negative positive ratio is shown to be ineffective, and increasing porosity is only marginally effective due to losses in overall cell energy density. For a loading cell with 3 million power per centimeter square, combination of operating at 45 degrees Celsius with electrolyte having reduced tautirosity, enable energy density of 186 and 102 watt-hour per kilogram during 4C and 6C constant current charge, and can be a very viable near-term technology. To further investigate the extreme fast charging enhancement from temperature, moderate loading cell was charged at 6C constant current CV for total charging time 10 minutes, and at 20 to 50 degrees Celsius, and the results are shown as dashed lines in the top figure. After 10 minutes charge, cell was discharged at silver 2, half C. Each cell was cycled 5 times at only 5 times at one temperature, and then cut open in discharged stage to visually inspect for lead-plating. The final SOC achieved at 20 to 50 degrees Celsius during the constant current portion of charging were 17 all the way to 52%. SOC, the final SOC during the 2 to 10 minutes charging, including constant current, constant voltage, 67 all the way up to 97% SOC respectively. Thus, increasing operating temperature actually significantly improve high rate charging acceptance. Bottom figure, actually this figure illustrated a lead plating condition after we open the cells. A large amount of lithium can be observed. This is a shiny silver area can be seen at 20 and 30 degrees Celsius. Conversely, very little lead plating is visibly detected for cells operated at 40 and 50 degrees Celsius. Similar results can be realized for 4 million per hour per centimeter square and non-conventional electrolyte high temperature. But the temperature is not 45 degrees Celsius. We need a 60 degrees Celsius. 60 degrees Celsius would require development of suitable coatings and electrolyte additives. Again, it's important to continue research on electrolyte with enhanced transport, something like 2 times ionic conductivity, 4 times diffusivity, and the transference number increased by increased to 0.15 will be ideal. Except improvement of charging acceptance and lead plating, elevated temperature will significantly impact battery life also. This is addressed by a physical-based surrogate life model of high quality, long calendar life. Commercial NMC graphite cells was used to analyze life benefits, detriments at high temperature fast charging. This commercial cell has a very good calendar life, and for this study we consider the cathode cracking mechanism and Arrhenius temperature dependence. We didn't address lead plating mechanism. Actually, the model was fit with silver 3 and 1C charge. So we're using it to predict the 6C performance. It's kind of a gross extrapolation, but just used to illustrative its purpose. The elevated temperature scenario we will explore the first is the cooling time constant. Actually, when you heat up the cell, charge the cell, you need to cool down the cell. How long it may take? For this case, we compare the 10 minutes and the 60 minutes. So the cooling time constant is the time to draw down the cell average temperature by 65. For this long calendar life battery during accelerated cycle life testing, 10 minutes cooldown has slightly life benefits versus 60 minutes cooldown. At 20% capacity feed, rapid cooldown, 10 minutes cooldown have 77% longer life. If we consider the real case scenario, for example, have 1,000 fast charging occurs over 10 years, 20% longer battery life can be achieved with a rapid 10 minutes cooldown. Trade-off is the cost of a larger battery thermal management system versus 2.5% larger battery to account for extra feed. This will decrease if the fast charger is more often, such as 1,000 cycles over 3 years. The benefit will be 70% longer life. Except the cooling time constant, other scenario will directly address the fast charging at a high temperature. The model estimated 150% longer cycle life when 6C charge compared to fast charging at 35 degrees Celsius. It's worth to mention the model account for cathode cracking and SEI growth, no depleting. We also see benefits. As mentioned before, depletion can be provoked with heterogeneity. Heterogeneous behavior becomes significant for large size cell. This 3D model captures the heterogeneity caused by non-uniform electrical and thermal field with a 3 parallel 2 series connected cell with a liquid cooled plate. It was found that electrolyte close to the tab area was preferentially used during charge. This is because electrical potential and also because the higher temperature, usually the cell has a lower resistance. As can be seen from this study, the cell heterogeneity is related with temperature non-uniformity, so the heterogeneity can be controlled by minimize the temperature difference. This can be achieved by enhanced cell thermal conductivity and the range heat transfer pathway more evenly, such as doubling the thermal conductivity of the cell and using fins on both sides of the cell. Additionally, optimal design of the cooling surface of the cell is necessary. For example, before there is only bottom cooling. Now, if we compare it with top cooling, tab cooling, so what it looks like. So as long as the heat was evenly distributed to its surroundings, significant heterogeneity mitigation can be achieved by cooling the cell on multi-sided as shown. Compared with bottom cooling, bottom and top cooling reduce the temperature and the depth of discharge difference within the module by 10% and by 10 degrees Celsius and 4% respectively at the end of 6C constant current fast charging. With additional tab cooling, this is more like a spot cooling. The depth of discharge difference can be further reduced by 3%. Supported by ARPA-E program, our group worked with industry and university partner to develop an active cell electrical management system, enabling cell differential control of strong cell versus weak cells. The 2-volt load is used to differentially balance battery cells. Low-cost isolated bypass DC-DC converter module connected each cell to the vehicle 12 bus. Existing DC-DC and battery thermal management is replaced with integrated modular BMS DC-DC. Life balancing lead to reduced capacity imbalance that can be caused by factors such as pack temperature gradient and slightly manufacturing variance among cells, increase lifetime and relax thermal management system. Range is no longer limited by the weakest cell in the pack. Proposed system architecture and life balancing was experimentally validated. For fast charging application, it's expected the life balancing will be more beneficial. Supported by Shell Game Changer programs powered by NR, and we have worked with OCL to develop and validate the battery pack prototype integrated with OCL's intelligent battery thermal management technology for fast charge application. This company designs and manufactures lithium battery pack for portable, stationary, and transportation application. OCL has a unique passive thermal management technology based on the use of phase change composite, a mixture of wax and porous graphite matrix to surround each lithium battery cell, absorbing and conducting heat away to extend the life of the cells and prevent fire and danger damage to the cell. To develop a working prototype for fast charging, this system should effectively control the cell temperature and minimize temperature non-uniformity. To develop a precisely calibrated thermal management system rely on accurate characterization of battery cell electrically and thermal behaviors. We used our isothermal battery calorimeter to determine the heat level and energy efficiency of a nickel-rich NMC cell. Except C rate, there are other charging parameters such as charging voltage windows. We also developed a model to predict the cell electrical behavior and the thermal behaviors at both load cycles and constant rate cycles. So the result has been used by OCL for PCC design and optimization. Quickly compared to Pack 1 and Pack 2, as you can see, Pack 2 the cell is relocated. The weight of phase change composite housing cases of Pack 2 is reduced by about 10%. And simulation result shows actually, as it can be seen, that this is a temperature difference of Pack 2. It can maintain the minimum temperature difference among the cells. To compare the long-term battery use strategies, we need a battery model analysis is crucial. This was achieved by NR's lifetime model. This model is a predictive model, extending expensive live battery agent dataset to real-world scenarios. Degradation mechanism, along with temperature and the cycling factors, are regressed to produce a lifetime prognostic model. By analyzing the agent data from OCL, moderate and fast charging cycle was distinguished. The criteria to distinguish moderate cycling and fast charger is not only related to charging rate itself, but temperature. For example, moderate charging rate are defined less than 1 C at 25 degrees Celsius and less than 1.5 C at 35 and 45 degrees Celsius. This is related to the concentration gradient in active material particle calculated by charging and discharging C rate times square root of charging discharge time. The middle figure shows the rate of the capacity loss per cycle as a function of a concentration gradient captured by a sigma model function around concentration 1. Concentration gradient 1, sudden damage occurs and the rate of capacity loss significantly increased. Sorry for the red box, but if this is a perfect testing condition for compare. Fast charging at 25 and 35 degrees Celsius, and the loss of rate was similar at 45 degrees Celsius. Low rate of feed can be achieved. Model regression indicates capacity feed at fast charging cycle is likely caused by lithium site loss. At moderate cycling, capacity feed was mainly due to lithium inventory loss. Considering temperature management is required for fast charging, a technology expanding the current use of phase change composite technology is proposed by Allcell. This is done by using the phase change material incorporated between individual cells as the resistive heater. This proposed technology will enable direct rapid heating of individual cell due to the pre-existing phase change composite lithium cell integration and thermal transfer concept already established without impact on energy density and cost from an increase in battery preheating components. The phase change composite will need to be designed to enable rapid preheating while still maintaining substantial thermal conductivity and latent heat characteristic for passive thermal management performance. Proof of concept for preheating was carried out with the 3D fundamental element simulation. The result demonstrated nearly 10 increase, 10 degrees Celsius increase can be achieved in about 10 minutes. With the phase change composite heating, a prototype experiment is in progress so far. Based on the study, besides the room temperature study, we have been working with OCL to broaden this technology for fast charging at sub-zero temperatures. Left figure shows the charge acceptance as function of charging C rate and charging temperature. In general, charging acceptance become worse at high C rate and lower temperature. At 0 degrees C, the charge acceptance is 50% with a 2C rate, indicating the cell still can be charged to 50% in about 50 minutes. However, the charge become much worse with 2C rate at minus 20 degrees Celsius. To charge the cell at minus 20 degrees Celsius, effective preconditioning by warming up the cell is necessary. It's worth to point out self-heating should be considered to work with the warm-up technology. The development of a fast charge capable lithium battery pack is a system level concern. All parts in the system, including the lithium battery cell, battery pack, battery management system, and thermal management system need to be optimized and carefully integrated. This flow chart representatively illustrates an intelligent battery thermal management system framework to analyze, control, and optimize fast charging capable lithium battery pack. The temperature of the battery pack will be increased before the charging step to improve the electrochemical kinetics while charging. The temperature will be limited by choosing the suitable wax or other phase change materials with the desired phase change temperature. The intelligent battery thermal management system would also be able to communicate with the charger based on the electrical and thermal status of the battery pack. Input to this battery charging algorithm will be cell, phase change composite temperature, state of charge, state of health, voltage, and current in an integrated management feedback loop. With that, please let me give you a summary of what I have been talking about over the last hour. First, we talk about the fast charging is limited by transport and damage, especially for high energy density cell. Ideally, next generation electrolyte with higher conductivity, diffusivity, transference number will be available. A combination of solution is probably a practical solution for fast charge to enable fast charge. Among these strategies, we evaluate the temperature control is very important for fast charging as a near-term technology. Effective method should warm up and cool down the battery efficiently. At the system level, minimize temperature heterogeneity is vital. Life-driven balance may become necessary. Recently, we worked with Allcell to develop a thermal management solution based on the phase change composite. It's promising this technology works for both normal temperature and sub-zero temperatures. And thank you for attending my presentation. And also I thank the support from the vehicle technology office at the US Department of Energy, and also Shell Game Changer program powered by NRAR GCXN. Thank you.
Great, thank you, Chuanbo, for a deep dive into the electrochemistry of lithium-ion batteries and impacts and solutions around fast charging. If there are any questions, you would have to type them into the Q&A box.
Yeah, I'd like to ask a question.
Yeah, great.
So thank you for very interesting talk. You showed that you can have lithium metal precipitation near the current collector when the electrolyte concentration goes to 0. Also, you showed that graphite can have lithium metal precipitation, and you showed this very nice optical imaging, which that's very compelling. But is there a way without looking inside, just from the impedance, that you can quickly tell whether it's scenario 1 or scenario 2 for this charge acceptance of lithium metal precipitation issue?
Yeah, here actually we try to develop this kind of technology, especially based is a model based, and if we can, this is some voltage loss, as you can see after fast charging during voltage relaxation. We calculated the impedance and the transport resistance. This is a transport resistance. As you can see at 4C, beyond 4C, there is a plateau indicating this cell was stopped charging due to the transport limitation. But this is perfectly working for a single layer cell. We try to apply this technology for cylindrical cell, commercial available cells, and found actually it was affected by the temperature a lot. So we need to do a lot of calibration before we use this method to determine if electrolyte, at least electrolyte behavior is a limiting factor or not.
I see. So this is still mostly a model-based estimation instead of like a direct visual validation of the model.
Yeah, actually we compare, as you can see, we compared with the testing result and the model result. Then we use model to see what's going on inside. So that's our approach. So it's a combination approach. Gotcha. Yeah, but yeah, still difficult to apply to the probably onboard analysis or this kind of thing.
Yeah, another question is Tesla, I think maybe 1.5 years ago already have this, before they reach the fast charging station, they would preheat the battery pack. So your work with Allcell, I guess, what is the key difference with the Tesla approach?
I think, thank you. That's a really good question. And yeah, I also aware about that. And the difference is, as you can see, we are doing the similar thing. When Tesla, if you tell the vehicle you are going to fast charge the cells, so they actually probably stop the thermal management system. Actually, purposely heat up the cell using the heat when you drive the vehicle, right? Here we wanted to, it's a little bit passive management, just utilize the heat generated during driving. But here we are talking about the technology to manage or control the temperature, to enable more higher fast charging, and also for low temperature application. So I think that's a difference.
Thank you, Dr. Yang.
Thank you for your question.
Great, thank you. I have one final question. When you do this tests in the lab, do your testing protocols, do they reflect a specific type of application of the battery? You know, I guess a battery will be used very differently in the grid compared to for transportation purposes. To what extent is that recognized in the testing in the lab?
You mean the work with our cell?
It's more in general terms, actually, when you test batteries in the lab.
Yeah, we support by the vehicle technology office. So usually our study is for vehicle applications.
Okay, for vehicle applications. Okay.
Yeah, but the work with our cell is for portable like drones and also stationary like fast charging stations.
Okay.
Yeah.
Okay, thank you. Thank you. Very interesting. I think in the interest of time, you should wrap up. We're a little bit over time here, so I'd like to thank all the panelists for excellent contributions, and also to thank all the audience as well for great questions along the way. Drew, do you have any announcements before we wrap up the session?
No, I think just thank you very much, Alden, for your excellent chairing of the session. I think it's a very interesting session. Yeah, we're just going to come back at 10:25. I think Professor Sarah Jordan is already here, and she'll take over at 10:25. Thank you.
Thank you.
Thank you.
Hi, Drew. Great to see you again this year. How are you doing?
Hi, Sarah. Very good. Good to see you.
Yeah, it's great to see all these familiar faces in the last session.